Hi guys. Today I want to kind of give you guys an introduction to solar system, to the planets. We'll talk more about this next week, but I want to just take a look at this data chart, which is on page 15 of your reference table. And if you want, just like we've done in class, we're going to highlight a few things, and I want to point out a few things, and then I want to talk about scale. So let's just start with a little bit of highlighting here. You can see all 8 planets that are listed on here. When I was your age and I was in 9th grade taking Earth Science, there were 9 of them. Poor Pluto is left out of the mix, and we'll talk about that maybe a little bit later on. But what I'd like you to do is I'd like you to take your highlighter and just highlight these first 4 planets. So don't highlight the sun. So Mercury, Venus, Earth, and Mars. I'm going to go like this, and then I'll just make this more transparent so you can see that a little bit better. Okay, so these are my first 4 planets. Now, the reason I'm highlighting those separately is because of their makeup, so their composition essentially. So these planets right here are called the terrestrial planets. And I'm going to write that right here if I can. I just do that with my marker. So these are terrestrial, T-E-R-R. Okay, terrestrial planets, and there are 4 of them. Now, why are they called the terrestrial planets? Because they have a rocky, solid surface. And the way you can kind of tell that based upon this chart is right here in their density. You'll notice that the 4 terrestrial planets are dense, right? They have a density of somewhere above 3, like 5.4, 5.2, 5.5, 3.9. That's their average density of the entire planet. Earth's density of 5.5 is like all the different types of rocks that make up Earth on average have a density of 5.5. And these have a nice rocky surface. Now compare that to the other guys, and I'm going to highlight the other ones as well. So Jupiter, Saturn, Uranus, and Neptune. I'm going to highlight those, and I'll do those a different color. Let me just change this to, let's make it orange, and we'll make this orange as well, and then we'll just make this a little bit more opaque so you can see that. So there are the other 4 planets, and these are called the Jovian planets. I'm going to write that over here. So Jovian, J-O-V-I-A-N, and you'll notice that these 4 planets are a lot less dense, right? 1.3, 0.7, 1.3, and 1.8. So their density is a lot lower. Jovian planets are also called the gas giants. They're made out of gas. There are some theoretical ideas about the core of these planets, like whether they're liquid or whatever. But for the most part, it's a big giant ball of gas. Okay. Now, why are they called giants? Well, that's right here in their equatorial diameter. You'll notice that they're much, much bigger. Obviously, Jupiter and Saturn, Jupiter being the biggest, 142,000 kilometers across. And I'm going to show you a picture of a little bit of scale in a second. But again, these are much larger planets. The terrestrial are a lot smaller. Okay, so denser, less dense. Bigger, smaller. Now, the other thing that's kind of key, obviously, the first 4 planets are a lot closer to the sun. So their mean distance from the sun goes up to 227.9 million kilometers away. So these are closer, obviously, and these are much further away. And we'll look at scale a little bit later on. Also notice something here that's related to that. We talked about this with ellipses. Obviously, when you get further away from the sun, the time it takes to go around the sun is much longer as well. So these 4 planets have a much longer revolutionary period. In fact, it takes 164.8 years, Earth years, for Neptune to go all the way around, okay? Which is kind of interesting. If you lived on Jupiter, fun fact, if you lived on Jupiter, you'd all be 1 year old, right? Because it takes 11.9 years to go around. You hit your 1 year birthday when you turned 11.9 years, basically, okay? So kind of an interesting fact. One thing also to take note of on here, obviously, you can see the mass of the planets compared to Earth. We'll say the mass of Earth is 1. Jupiter is 317 times more massive than Earth, so it's obviously really big. Look at that compared to the sun, which is 333,000 times more massive, and we'll take a look at that a little bit later on as well. But all of this data on here is interesting. One last fact that I'll point out, the period of rotation is how long it takes to rotate, so it's 1 day. Obviously, Earth rotates once every 23 hours, 56 minutes, 4 seconds, so basically 24 hours. That's 15 degrees per hour, right? We've done that math before. But notice the period of rotation of the big giant gas giants here. They are spinning a little bit faster, right? If you look at Jupiter, it spins all the way around once in almost 10 hours, which is kind of crazy. Its spin is so fast. That's actually what causes all of those, you'll see like the big giant red spot on Jupiter. There's a lot of swirling gas, which is going to create kind of tornado, hurricane-like conditions on the surface. So that fast spin is interesting. Look at the spin of Venus. The spin of Venus is 243 days. So in other words, 1 day on Venus is actually longer than 1 year on Venus, which is kind of interesting. Which, if you think about that, that means every day is your birthday on Venus. Kind of cool, right? So anyway, there's some really cool things on here, some interesting facts, and I'm going to give you some questions today or next week to answer about that. Okay, so that's the initial part of this. And next I want to talk about scale. All right, so I've come back to our old friend, the Solar System Scope Simulator. One thing I want to just point out here is this is great for kind of simulating how things are moving around the sun. I'm zoomed in right now with everything fast forwarded. You can see this planet coming around, that's Mercury, which is moving obviously in its path around the sun a lot faster than the other planets because it's the closest, and you can see that on your reference table. Venus obviously kind of going a little bit slower than Mercury, but faster than Earth. Earth is coming around here. And then we have Mars. We have the asteroid belt, which is rotating as well. The asteroid belt is between Mars and Jupiter. And some of these asteroids have been kicked out from by Jupiter and gotten into orbit that way. Here's Jupiter down here. You can kind of see it coming around slowly. It takes 11.9 years for that to go all the way around once. Okay. And then Saturn and Uranus and Neptune. So we've looked at this already. One thing I want you to take note of, obviously this is great for looking at speed and rotation and all that stuff, but it is in no way drawn to scale. And that's kind of misleading. Like you might think, oh, there's the Earth, there's the Sun. How could you like compare the sizes of these planets to each other and how far away they are? And so I want to show you guys a picture that puts them all in the same frame, but to scale. So these are the planets drawn to scale. So you can see Earth, this is Venus, and this is Mars, and this is Mercury, and that's little Pluto, which is not a planet anymore. Uranus and Neptune, Saturn without its rings, and Jupiter. So just compared to each other kind of gives you a little bit more perspective there about how big they are, and just think about how minuscule you are. Kind of makes you feel a little bit tiny, doesn't it? Now, obviously, Jupiter is huge, comparatively speaking. But let's compare this to the sun. So if you actually look at the sun in the picture, wow. Yeah, so now you're thinking, well, that's kind of crazy, right? There's little Jupiter compared to the sun, and there's a tiny speck of Earth, right? So it just kind of putting things in perspective as to the actual size of these things makes you feel a little bit like, wow, I am very insignificant. But in the eyes of God, just remember that you're not. He knows all the hairs on the top of your head. So that's kind of a comforting thought as well. So just scale is important. The other thing that's important is distances. Obviously, compared to each other, you can see how small the Earth is. But let's just look at distances a little bit. And I'm going to put a video on the agenda for today, which kind of scales out the solar system, and it was done by Mark Rober, so it's a really well done video. But I want to show you guys a little kind of a cool calculator thing. So I'm putting this link on the agenda for today. This is a way to kind of look at scale of the solar system, and you can type in any numbers you want. So I put in, let's say that the sun is a 12-inch diameter. So imagine a ball that's 12 inches. A basketball, by the way, is about 9 inches. So just a little bit bigger than a basketball. All right, and I'm just going to type that number in there, and I'm going to hit calculate, and it will calculate these numbers automatically. It crunches all the numbers. So it tells you how big the planets are compared to our 12-inch diameter sun. And so that's kind of cool. It puts that in there. But it also gives you distances, or the radius of the orbit. So how far away is the planet from that 12-inch sun? And what I did when we were in school, I used to do like a scavenger hunt, and I'd put all these planets out. So just to kind of give you guys an idea, this is a 12-inch sun, and these are all the planets compared to it. Okay, so you can see how small they are. I hid all of these planets all around the campus of school. The only ones I did not hide were Uranus and Neptune, because they would be way off campus. But these I just hid around the school, and if you found one, I gave you an extra credit point on your marking period average. Obviously, we can't do that anymore, but it was kind of fun. Just to give you guys some perspective, Saturn, I put the sun in my classroom. Saturn was on the football field, like actually in the bleachers of the football field on the upper field. So kind of crazy. It's tiny, and they had to find it. It was a magnet. It was stuck to the side of the bleachers. Anyway, so this is just kind of a little bit of scale. What I'd like you to do, and this is something that I'm not going to require this. I'm not going to say you have to do this, but this maybe is your activity for today. Get outside, okay? And I want you to walk to Pluto. All right, so what do I mean by that? Well, let's make our sun 12 inches, and let's start with Google Earth. And I'll put this link in Google Earth. But if I were to do scale, so I'll give you the link. There's this little ruler down here, okay? And if I put that, and you can put this on your house or whatever, just zoom into your house, find it. I'm going to put it on the classroom of CBA, my Earth Science classroom. I'm going to click there, and I'm going to bring this out. Now, I know from my calculator that Pluto is 1294 meters away. So if I can maintain that distance in meters, let's change this to meters. I'm going to go 1294 meters away from the classroom. So obviously Pluto is way off campus. In fact, if you were to walk it out, you would end up like at Nottingham High School to walk to Pluto, just to give you a perspective idea, right? If you were to do Saturn, for example, I said it was on the bleachers. It's right around here. And if you look at the scale, Saturn is 312 meters away. So on our scale, 312 meters, you can kind of see it on the screen. It ends up being right around here in the bleachers, okay, from the classroom. So that's kind of a fun little activity. And you can do that at home. You just find your house, click on your house, and just stretch out that ruler as far as Pluto and go walk there and then back or something like that. It'd be kind of a fun thing to do. I might do that later on today. So that's one thing to look at. And here's another thing about scale. Our solar system is obviously really large when you go out to the outer planets like that. But what about other stars? The closest star to us is a star called Alpha Centauri. Okay, it's super far away, like 4.5 light years. But on our scale model, the sun would be another 12-inch sun or so. On our scale model, it's 8,846 kilometers away. So just to kind of give you an idea of how far that is, let's change this to kilometers. 8,846 kilometers. Well, which way do we want to go? North, south, east, or west? Let's go across the Atlantic, okay? So 8,804, oh boy, we're going really far away, okay? In fact, you'd end up like at the Nile Delta over here, okay? Just to give you an idea of how far away the next star is. That's the closest star. And obviously there's other stars out there that are much further away. The Mark Rober video I'm going to give you today to check out gives you a little other idea about the scale of the universe. Watch all the way through to the end of the video. He'll talk about the Hubble telescope image of all the other galaxies that are out there, and it's a pretty fascinating thing.
To think about it another way, there are more stars in the universe than there are grains of sand on all the playgrounds, beaches, ocean floors, and deserts on our planet.
So anyway, I'm going to leave it at that. Your task for today is, go outside and walk to some of the planets if you want. Use the Google Earth simulator here and try to figure out how far away they are. a not required thing, but it'd be a worthwhile thing to do. Okay, so that's it, and I hope you guys have a great day, and we'll be talking more about the solar system next week.